Welcome back. In this lecture, we discuss again with regard to one dimensional heat equation two important properties of the solutions, namely weak, maximum and minimum principles. Such properties are also enjoyed by the solution of the Laplace equation. So, in fact, the solutions of the heat equation share this property of the solution of the Laplace equation. So, first let us fix some notations. So, let T be positive and denote by omega t this open set 0 L cross 0 t. So, 0 L can be replaced by any open interval on the real line. For simplicity, I have just taken it to be 0 L. So, let me draw the diagram. So, this is 0 L. Okay, so, let me use different color here. And this is the level. Let me just t equal to t. Let me remove this. T equal to t and this is t equal to 0. So, the boundary of this open domain consists of 4 lines. So, here I have put 2 red one black and blue one. So, these 3 lines. Okay, so, what is omega t closer? So, that is simply 0 L zero t. Now, you consider the union of these 2 red lines and this black line. Okay, denote that by del p omega t. So, this is union of. So, let me just write of the interval 0 L on t equal to 0 and boundary lines on x equal to 0 and x equal to L shown in the red color. So, this has a name, this is called. So, we are omitting one part of the boundary of omega t, namely this the line t equal to t. So, this is referred to as parabolic boundary. Of omega t. So, its boundary minus that one line segment on t equal to t. Okay. With these notations, now we state the theorem. So, these are weak maximum and minimum principles. So, theorem. Suppose u is a continuous function on omega t bar, so including the boundary. So, since this is a compact set, then you will be bounded on omega t bar such that it is just like the previous theorem. So, the first derivative with respect to t exists and the second derivative with respect to x exists and they exist. So, this is the hypothesis and are continuous. Okay. In omega t. Okay. Then the following hold. The following hold. There are three statements, conclusions. The first one, if u sub t minus a square u sub x x is less than or equal to 0 in omega t, then maximum of u in omega t closure, as I said, it is a we are assuming it is a continuous function. So, it is bounded and this is less than or equal to maximum of u on the parabolic boundary. That is I suppose that was our notation. Yeah, del p omega t. Okay. Of course, this does not rule out that u may attain its maximum even somewhere in omega t, okay, but it will not be more than the maximum that occurs on the parabolic boundary. If now we change the sign here, u t minus a square u x x is bigger than or equal to 0 in omega t, then minimum u in omega t bar is bigger than or equal to omega t. And finally, equality. If ut minus a square uxx equal to 0 in omega t. So, u satisfies the heat equation in the domain omega t, then so you combine these two. So, you get maximum of mod u in omega t bar is, no sorry, I am sorry for statement. So, this is equality. Okay. So, before proof just uses the ideas of the calculus, it is not very difficult. So, I will provide a proof of this, but before proving the theorem, so comments. The theorem we obtain uniqueness. Okay, let me not write 1, that may cause confusion. So, first comment is uniqueness follows, uniqueness of the initial value problem for the heat equation follows. And the another advantage of such uniqueness results is that if we try to find a formula for the solution by some method, either Fourier series, Fourier transform, then we need not worry about uniqueness. Uniqueness is separately proved. So, that is why such uniqueness results, they play an important role. Okay. So, this just one comment. So, another comment I just okay. So, regarding the proof, so first some observations. So, suffice is to prove statement 1. So, this is the first observation, prove statement 1. Why is that? For statement 2 follows from 1 replacing u by minus u. Just see here, if I change u to minus u in the second statement, that then we get this inequality. Okay. So, if we are already proved this one, then we can apply. So, this then you get maximum of minus u and maximum of minus u, and that becomes minimum, minus of minimum. So, 2 follows. and 3 follows, again statement 3 follows by applying 1 or 1 and 2 if you like, applying 1 to both u and minus u. So, when there is equality here, there is equality here. So, it is both less than or equal to 0 and greater than or equal to 0. So, I can apply again statement 1 to both u and minus u, and then that results in this statement. Okay. So, it suffices to prove just statement 1, that is the observation. And just remember, in the statement we are not using any formula for u. U is any continuous function satisfying these properties. Okay. So, we are not referring to any Fourier Poisson formula or any Fourier series, anything. So, that is why such results are important in the analysis of PD. We always look for such results. So, as general as possible. Okay. So, proof of 1. So, define. So, now we are considering an auxiliary function. So, define. So, this means what? We are assuming u t minus a square u x x is less than or equal to 0 in omega t. So, define p of x t is u of x t plus epsilon x square. So, epsilon is a small positive number. So, then you compute V t minus a square V x x. This is same as u t minus a square u x x. With respect to x, there is another term coming here, namely 2 epsilon, and there is a square there. So, you get minus 2 epsilon a square, and by assumption this is less than or equal to 0. So, this is less than or equal to 2 epsilon a square, which is strictly negative in omega t. Remember that. So, now assume V assumes, okay, assume suppose V assumes a maximum at x 0 t 0 that does not belong to the parabolic boundary. So, we want to obtain a contradiction. What we intend to show is the maximum of V can occur only on the parabolic boundary. So, we are assuming this x 0 t 0 is somewhere here, where the function V assumes a maximum. Okay. The t 0 can be on the blue line. Okay. So, I am not ruling out that, but I am assuming it is not on the parabolic boundary. So, these two red lines and this one black line. So, t 0 could be on the blue line. Okay. Just remember this diagram. Then from the calculus we see that V t x 0 t 0 is bigger than or equal to 0 and V x x at x 0 t 0 is less than or equal to 0. A comment about this, though it is first derivative, I am not putting equal to 0, it is equal to 0. So, let me just make that point separately. V t x 0 t 0 is 0 if t 0 is less than t, but if this point lies on the blue line, that means t 0 equal to t, then we can only claim this is bigger than or equal to 0. Okay. That's enough for us. Okay. So, at that point x 0 t 0, where we are assuming V takes a maximum which is not a point on the parabolic boundary, then this first derivative with respect to t is non-negative and the second derivative with respect to t is non-positive. Okay. But then we get a contradiction. So, at x 0 t 0 V t minus a square V x x. So, this is non-negative, this is non-positive, but there is a negative sign here. So, this quantity is non-negative, but we have just shown by hypothesis that it is strictly negative. So, this is a contradiction and shows that we can attain its maximum certainly it does, because V is a continuous function and we are in a compact set. Maximum only on so what we have proved for V is referred to as strong maximum principle. Okay. Such a claim we cannot make for u, that is why we call it weak maximum principle. So, these are again important results in the analysis of heat equation, which provide uniqueness and comparison results. Some of them we will see. Okay. So, as I against the we have stated weak maximum principle, but what we have proved for V is referred to as strong maximum principle. So, we can attain its maximum only on the parabolic boundary. So, if we can make such a statement for u also, then it is referred to as strong maximum principle, and from this we will obtain the result for u. How is that? That is just one step. So, we have, so since epsilon is arbitrary, so let epsilon tends to 0. So, then we see that the first and the last term of this chain of inequality are the same. As epsilon tends to 0, this term goes away. So, I have maximum of V over the parabolic boundary, and here also maximum of V over the parabolic boundary. That implies equality should be there everywhere. So, in particular, so we obtain maximum of u omega t bar same as. So, as you see, it just uses some simple calculus results to prove this result, which is important in many aspects. So, let us see some consequences. So, first is uniqueness as usual. So, again you consider the heat equation. So, u x 0 is g x, and since these are boundary values, so just provide 0 t equal to some h 1 t u l t h 2 t. So, t positive, x is in the interval 0 L, and this is in omega t. Okay. So, claim is one has at most one solution. So, we are not claiming that one has a solution, but if it has one, at most one solution, then that is unique. So, again if there are two solutions, you take the difference. If u 1 and u 2 are solutions, two solutions, apply weak maximum principle. Okay. To u equal to, again you take the difference to conclude u is identically 0. That gives you uniqueness. Comparison, what is comparison? So, now you consider problems with different initial values and possibly different okay, for simplicity just let me take same thing, but you can take different things just for writing things, and you also take another one, another initial data. So, comparison means, so if G 1 is less than G 2, then you get corresponding solutions. So, let me call it U G 1, U G 2, corresponding solutions. Okay. So, you can also take different boundary data, and if some inequality holds between them, then the solutions, corresponding solutions will also maintain that inequality. So, these are called comparison results. So, they all follow from this either weak maximum principle or weak minimum principle. We can also consider the inequalities in the equation. Okay, that is also possible, because inequalities are allowed in the statement of the theorem. So, there are many more interesting results. So, because of lack of time, we will provide some of them in the notes, but now we will proceed to find solutions of this heat equation in a bounded interval using Fourier series. So, we consider again different kinds of boundary conditions, namely Dirichlet, Neumann and mixed ones, and see how we can apply the Fourier series method in order to find the solution. Thank you.